Hey, good morning, guys. So this is our second last lesson out of kinematics. Both these next two lessons are going to deal with projectiles. Some of this should be review from 11, and some of this will be a little bit new, but not a lot new. Just going to be combining the vector stuff with stuff you've seen before. So it should be straightforward. So projectiles you've seen before. Projectiles an object in free fall. You've studied one-dimensional projectiles. We're going to do two-dimensional projectiles. So it's 2D. It's not that much harder. So I've got a mass held at shoulder level and it's fired horizontally. So it's given a horizontal initial velocity. The curve that shows the best path, if you were here, we'd talk about it. But the curve that shows the best path here is B. And if you look at Y, obviously this thing's not going to fall straight down because it has a horizontal initial velocity. It's not going to go all cartoony and go straight over and then drop because gravity is going to start to act down on this thing. And it can't be C because gravity is going to start to act right away. It's not going to have any purely horizontal piece to it. So it's got to be B. Because gravity always acts. And this is something that's important to remember because students, you'd think that would be common sense, but students often forget that. So you can't have any flat path. Example 2, this is another common misconception. If I have two identical objects held at the same height above the ground, object 1 is released and on falls to the ground. Simultaneously, object 2 is projected to the right and it falls to the ground. Which one hits the ground first? I've had lots of students argue various things. Some say it's object 1 for this, and this reason. Some say it's object 2 for this, and this reason. But what's important to acknowledge here is that the horizontal velocity is completely independent of what gravity is going to do, and gravity is going to act on these two objects equally and identically. Gravity will act on both objects the same. Now, I think where people get confused is they say, well, yeah, like a paper airplane, or I don't know, it's always the classic one. You can throw things and they'll stay up longer than they would have if you had just dropped them. Yeah, that's true, but then you're bringing in extra physics. We don't want to talk about lift. The point is not to talk about is not the lift in an example like that. The thing that it's important to recognize is that gravity acts on objects the same whether they're moving horizontally or not. So they should both hit the ground at the same time. Mythbusters did a fantastic video. If you were in class, we'd watch it, involving a handgun and a bullet dropping mechanism. Basically, the handgun and the bullet were dropped. Handgun was fired almost at the exact same time the bullet was dropped. There is experimental, there's error introduced here, but they actually show on slow motion, like super slow motion camera, that a bullet fired horizontally and a bullet just dropped next to the gun at the exact same time, hit within milliseconds of each other. And I'll post the video with this lesson. It's really, really quite cool to watch. If you guys haven't watched any Mythbusters, I would encourage you to, if you're curious about the way the world works. Some of their stuff is ridiculous, but it's all awesome. I'll post that. They hit the ground at the same time, effectively the same time. So you've seen this before, but it's important to remember that your Vx is constant always. The gravity, acceleration due to gravity doesn't change this. But Vy is changing. Well, why? Because acceleration due to gravity is equal to negative 9.8 meters per second squared due to gravity. So I got something looks like this. We can plot Vx and Vy all throughout it. Vx is going to remain the same length. It's going to be constant. It's going to look like this, even as it hits, right before it hits. It's going to have constant Vx. Now we can look at Vy. Vy is going to shrink as it rises. It's going to be Vy. It's going to be 0 up here at the top. you're going to have Vy start to drop down here, and you're going to have Vy. Now, this thing hasn't hit the ground yet. Yes, I know. A whole bunch of you will say things like, oh, but it hits the ground and Vy is 0. Like, well, no. That's a different part of the problem. Then it has to decelerate, and you have to handle that part of the problem differently. The Vy at impact is the same as the Vy at launch, assuming that the impact and the launch are level with each other. Equal and opposite if level. Vy right here is 0. Same thing with these two. Because they're at the same height, they're equal and opposite there as well. Velocities are always equal and opposite when they're level with the trajectory up versus the trajectory down. Flip the page. Just going to try and motor through this as quick as possible, because lots of this is review. The last couple examples are going to be more interesting. So we're going to indicate some velocity components on this projectile. Now we're launching this thing up at an angle, so things are going to be a little bit different here. Let's label some stuff. We're going to have a Vx and we're going to have a Vy. Vx and the Vy. Let's talk about what's going on here. Now the Vx, we've already established, is going to be the same all the way through. Vx, Vx, Vx. What's some other stuff that we know? At the top, well, what do we know? There's two things that we know. We know that Vy is equal to 0. It's just a few, yeah. I'll just say this in here. Acceleration is always negative 9.8 meters per second squared. I'll call this acceleration in the y direction. Always. In this problem. So we've got an object here. Now when it's even with launch, we know that the Vy here is going to, the Vy is going to equal negative Vy initial. I'll call this guy Vy initial. Our displacement in the y direction here is 0, and the acceleration in the y direction is still negative 9.8 meters per second squared. And then just before impact, we know if this height here is h, then my displacement in the y direction is negative h. Horizontal speed, that Vx, is constant because acceleration in the x direction is 0, and the vertical speed is always changing because the acceleration in the y direction equals negative 9.8 meters per second squared throughout the entire problem. Horizontal and vertical motion are independent of each other. I can never remember if independent's A and T or E and T. If I get it wrong, you know. Spelling is not the biggest part of the problem here. Okay, we're going to skip example 6. We're going to go straight to a real version of the problem. Here we go, example 5. Sorry, example 7. This is the kind of problem you should look at in Physics 11. We want to break a problem like this up because horizontal and vertical components are independent of each other. We break them up using a chart. We have horizontal components, we have all of our vertical components, we write them out, and we use these things to solve our problem. There is only one part of the problem that can reach over from side to side, and that is time. Time is not independent. Time is universal. So we've got that's the only piece that's gonna reach over. So let's fill this thing in. I've got a VI in horizontal direction or in the x direction. Vertical is the y direction. So VI in the x direction is 20 meters per second in this problem. Acceleration is 0. VI in the y direction is 0. My acceleration is negative 9.8 meters per second squared. I'll put units on everything. And if this thing's dropping all the way down to the bottom, my d is going to be negative 50 meters because this thing's dropping down. Now we can add some more stuff. That's what we know. Let's add the stuff we don't. I don't know my horizontal distance, and I don't know the time. I don't know if I care what my final velocity is here, so the only thing we're looking for here is time. So we know these two have to be equal. Time is universal. Different parts of the problem don't exist in different time frames. When we get to special relativity, that's not true, but in an inertial reference frame, which will make sense later, time is universal. So we can use the information we've got here to find t. We're going to use this kinematic equation here. This should all be reviewed. D equals VIT plus 1/2 AT squared. VI is 0. Negative 50 equals negative 4.9 T squared. T is equal to 3.19 seconds. You can do that calculation yourself just to verify it. Now, if that time vertically is 3.19 seconds, then time horizontally is going to be 3.19 seconds, and we can use this to find the range. Well, we've got no acceleration here, so this is just going to be a D equals VT problem. It's 20 times 3.19, so D is equal to, D in the x direction is equal to 63.8 meters, and we're done. This is stuff you did in Physics 11, or should have done in Physics 11. Let's flip the page, let's do another one. Example number 9. We're going to do a couple of them where we're going to launch them at different angles. Yeah, we'll launch them at different angles. We're going to start level, over level ground in launching these things. And then we're going to go to a cliff and launch these things at some angles here. So here we go. We skipped example 8. Forget example 8. We're just going to go straight and do the meat and potatoes of it here with example number 9. So for this situation, we've got a 100 meter per second projectile launched upwards at 35 degrees. It's going to land level here somewhere, and we want a few things. We want the time to the top. We want the total flight time. And we want the range. Okay, so before we do anything, let's fill out what we know. Do we know anything about the horizontal? No. We don't. We don't know anything yet, except that horizontally, my acceleration is 0 meters per second squared, and vertically, it's negative 9.8 meters per second squared. At this stage, that's all we know, because we need to break this vector up now into components, which you've seen before. We did that last week in one of the lessons. So here I'm going to have a Vx initial, and I'm going to have a Vy initial, and I'm using subscripts there to represent those things. Now, Vx initial is going to equal 100 cos 35, and this Vy initial is going to equal 100 sine 35, and if you're not sure why that is, we need to do some trig review. Either come see me, or you can go do some trig review on your own. 100 cos 35 is 81.92 meters per second, and the Vy component is 57.36 meters per second, so I want to add that to our chart down here. 81.92 meters per second and 57.36 meters per second. Now we want a few things. We want the time to the top, the total flight time, and the range. Now, let's write in some stuff. Actually, you know what? No. We're going to start to work through the problem, and then we'll add in the things we need. So, 1. We want time t-top. T-top equals question mark. So at t-top, what do we know is true? At the very top of the arc of this thing, we know a few things. We know for time top, and I'm color coding these different parts of the problem. We know that Vy top equals 0 meters per second squared. And we know that, well, I guess I've labeled it 2 different times here, but t-top I'm going to put as part of the vertical portion of this problem, because the time it takes to get to the top is a purely vertical thing. It's however long it takes gravity to slow down the vertical component to 0. So we can use kinematics for this. We're going to use this equation here. VF equals VI plus AT. VF equals 0. VI equals 57.36 meters. I don't need to put units right now because it's shoving into a formula. Plus negative 9.8 times time. So you can verify that the time here is, oh, what did I find? Found the time to the top. 57.36 divided by 9.8 is 5.85 seconds. Now we do that because this thing's level. We're going to do total flight time. Now I could set this up two ways. Because this thing's level, we know a few things. We know that Vy are at the end, because this is level, is going to equal negative 57.36. Maybe I'll make a note here, because it's level. Okay, so we could set this up two different ways. We could use VF equals VI plus AT. We could plug in our negative 57.36. Our VI would be positive 57.36, and our acceleration is negative 9.8. We could find it that way. Or we could recognize that total flight time, T total, equals 2 times T top, because it's level, which equals 2 times 5.85, which gives us a total flight time of 11.7 seconds, which we could then go to the range and say, okay, well, 3, I want the range. That becomes the horizontal component problem. The range is all about, how fast is it going in the x direction and how long is it moving in that direction. This is going to be d equals vt. My horizontal velocity is 81.92, and my time is 11.7 seconds, which is going to give me a horizontal flight time of 959.28 meters. And that's it. So even this first kind of question, you didn't look at it in Physics 11, at least that's what Mr. Morrison told me, but it's relatively straightforward. It's stuff that you've seen before. When things are level, even when we were doing just things flying straight up and down, whenever the projectile is level with a previous version of that projectile, they have equal and opposite velocities. That's what we did here. At the top of a throw or an object in free fall, my velocity is 0. So these are truths you've seen before. Nothing really remembered here, or nothing new here really. So there's a couple different strategies that we can look at here. For handling these kinds of problems, and I'll show you what some of them look like. Basically, you can go from where the object starts to the top, and then from the top to the bottom. That's a valid strategy. You can go from the top all the way down to the bottom. This one is going to require you to use the quadratic formula. And this one just here is a bad idea. Do not use. And I know some of you are going to use it anyway, because when I say things like that, just you do it anyway. But don't do it. I would encourage one of these two. This one, again, more work, but the math is less complicated. This one we bring in the quadratic formula, but it is ultimately less work. So one of these two strategies is what I would encourage you to employ here moving forward. So flip the page, here we go. We are going to I set this up a little bit differently last year. Okay, yeah, I'm going to do 10 and I'm going to do 11. So here we go. First, we're going to use strategy 1, the sum of the rise and the fall time. And then I'll show you what it looks like to do it just from beginning to end. So we want to find the flight time, and we're actually going to find the range here too, and range, because it is just one more step. So regardless of what strategy you choose to employ, we've got to break this thing up into horizontal and vertical components. So let's make the chart. Horizontal and vertical. Now we're making the chart ourselves, so I'm going to start adding some subscripts in here. I want VIX, I want AX, I want VIY, and I want AY. AX is always 0 meters per second squared. AY is always negative 9.8 meters per second squared. Now, if I look at the problem here, I've got 50 meters per second at 30 degrees. So I can break this thing up into a VX initial and a VY initial. It doesn't matter if I say VXI or VIX. I should have been consistent, but I'm running in pen, and I'm sorry, I've already screwed that up. So we can see here that this is where the 90-degree angle is. This side is adjacent. This here is 50. So that's the hypotenuse. So VXI or VIX, whatever, I'll just change it down here. VXI, VYI, there, fixed, is going to equal 50 cos 30, and this one's going to be equal to 50 sine 30. So those are going to be 50 cos 30 this is 43.30, and 50 sine 30 should be 25. Good. So we're breaking this thing up. So we want to find the sum of the rise time and the fall time. So we're gonna have two parts of this problem. We're gonna have the top, and then we're going to have the top to the bottom. So that's stage 1, and then stage 2. The top to the bottom. So, number 1, here we go. We're going to find the time to the top. We want T top. So we know that VY top is equal to 0. So T top is going to equal what? T top equals V final equals V initial plus AT. V final equals 0. V initial is 25 plus negative 9.8 times time. It gives us a time of, brackets there, it gives us a time of 2.55 seconds. T-top is 2.55 seconds. T-top, I'm just going to add it. I'm just going to put it everywhere. 2.55 seconds. And now I want the time from the top to the bottom. T from top to bottom. Now there's a few things that we've got to write in here. We've got to acknowledge that to go from the top to the bottom, V y top is equal to 0. We have the acceleration. This is going to be our initial, for stage 2, this is going to be our initial speed. I don't have a VY final, and I don't have a vertical, but so VY bottom equals question mark. That's our final speed. dy, I don't have that either, because this one's top to bottom. Oh, sorry, a little bit. So what we need to add here is we actually need to find the displacement or the total height. I want to find here the distance to the top. So the displacement to the top is going to be, we can use oh, we've got the time here. So we can just go like this. D top equals, which kinematic equation do I want to use here? There's a few I could use. I don't know. Let's use this one. VF squared equals VI squared plus 2AD. VF squared is 0. VI squared is 25 squared plus 2 times negative 9.8D. So D top is going to equal 25 squared divided by 2. That's going to give us a maximum height, D top, of 31.89 meters. So then our dy for section 2 is going to be this height of 60 plus this height here of 31.89. So that's going to give us a dy of 31.89 plus 60. It gives a dy of negative 91.89 meters. It's negative because this thing's falling from the top down to the bottom. We're ignoring what happened at the beginning. We're just going top to bottom. So we're going to use this formula here. We don't know the Vy at the bottom, so we can't use any kinematic formulas that use V final. So the only one that we can use is this. D equals VIT plus 1/2 AT squared. And remember, this is top to the bottom. At V top, it was 0. So that's our initial speed. This guy's gone. So we can fill in the rest. Negative 91.89 is going to equal 1/2 negative 9.8 T squared. All right, let's let that down. So this is going to give us negative 91.89 times 2 divided by negative 9.8 equals square root. My answer, it's going to give me, I got a time here of 4.33 seconds. So that's the time, the top to the bottom. So I got 1 and 2. The total time, or T total, is equal to 1 plus 2. That's going to give me 2.55 plus 4.33 equals 6.88. I didn't need a calculator for that. That's embarrassing. 6.8 seconds. And I can find the range easily enough. Find the range. Range is, horizontal distance traveled. That's range. All we're adding to that is this idea that our horizontal components are independent of our vertical components. So I've got D equals, or D, our range, is equal to VT, because there's no acceleration. We know the velocity there was 43.30, and now we know the total time it traveled horizontally is 6.88 seconds. So that is a horizontal horizontal distance of 43.30 times 6.88 equals 297.90 meters. We've got our total time. We're done. Okay. That's what it looks like to break this thing up into 2 different parts of the problem. Now I'm going to show you what it looks like to the exact same problem. So flip the page here. We're going to do example 11. I'm going to change the numbers so the numbers are the same, just so you can see that both methods are valid. So we're going to make this, and it's not 20 meters anymore. We're going to make this a 60-meter cliff. This is not 35 meters per second at 20 degrees. It's going to be the same as the previous question. This is going to be 50 meters per second at 30 degrees. And we're just going to use strategy 2. We'll just go from the beginning of the problem straight to the end of the problem. We're not going to break this thing up. And again, I'm changing the numbers to be exactly the same as the previous example so we can see our answers lining up. So we've got a horizontal. We still need to break it up horizontal and vertical. We've got a Vx initial and a Vy initial. A Vx initial, Vy initial. We've got an Ax and an Ay. Ay is negative 9.8 meters per second squared. Ax is 0. Vx is 50 cos 30. And this is going to be 50 sine 30. This is 25. And this one was 43 point something. This one was, let me flip back, 43.30. Okay. Now, instead of breaking it up, we're not going to go top to bottom. We're going to go straight to the end of this thing. So we know a few things. If we go straight to the end, we know that our dy is negative 60. We don't care what happens in the middle. We're just going start to finish. Okay. We are going to, yeah. And so now we want to find the time, total time. So we're going to use d equals VIT plus half AT squared, and we're going to fill in this information. Now d is negative 60. Our VI in the y direction here is 25 times t plus 1/2 negative 9.8 t squared. So this is going to be negative 60 equals 25t minus 4.9 t squared. And I want to move everything over to the other side, so I'm going to get 4.9 t squared minus 25t minus 60 equals 0. And now I'm going to use the quadratic formula. Actually, there's two different ways you could do this on your calculator. If you have a graphing calculator, graph it. If you don't have a graphing calculator, the quadratic formula, which you should all be familiar with it at this point. Quadratic formula looks like this. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. We've got it on our formula sheet now, so let's just use it. Negative b, so that's going to give me negative times negative 25 plus or minus the square root of negative 25 squared minus 4 times 4.9 times negative 60 all over 2 times 4.9. And these shouldn't be x, these are t's. These are time values. So I'm just going to simplify this here a little bit. This is going to be t is equal to 25 plus or minus, now we're going to get negative 25 squared minus 4 times 4.9 times negative 60. And I'm going to square root that right away. So it's going to be 25 plus or minus 42.44 all over 9.8. So we can see here that we're going to have the plus and minus, again, a bit of a review. We can take the plus solution, so 25 plus this divided by this, or we could take the 25 minus this divided by this. We should be able to see here, though, that 25 minus 42.44 is going to give us a negative time. Negative time doesn't make sense. So what we want to do when we're using the quadratic formula is to take the positive solution here. So we're going to find that t is going to equal 25 plus 42.44 divided by 9.8. Now we're going to find that T total equals 25 plus 42.44 divided by 9.8, and that's 6.88 seconds. Which, shock of all shocks, is exactly what we got before. It's actually really relieving when it works out that way, because that means it didn't make a mistake. So there it is. Now we can go back and find the range the exact same way. The range d equals vt. Horizontal velocity is 43.30. Our time is 6.88, giving us a horizontal displacement rather of 297.90 meters. We're done. So again, I don't care if it's way less work to use the quadratic formula. The other one is the mathematics arguably is simpler, but the reasoning it through is a lot more complicated. We break it up into part 1 and part 2. We find the time for part 1, the time to the top, and then we have to find the time from the top to the bottom. To find the top to the bottom, we need to find the displacement to the top, and then we have to find, then we have to add it together, and it's going to drop, and we have to find the time. And you can do it this way. There's no issue here. The math is simpler, but there's more steps to it. Here, we use one slightly more complicated mathematical formula, but there's way less work on my page, and I didn't have to change my drawing. So that is how I would encourage. I mean, this obviously is the way I like to do it. I don't particularly care how you choose to do it. You've got to find a way that you're comfortable with and that works for you, and that is so much of physics. There isn't a cookie cutter way that everyone has to do it, depending on your math skills, depending on the things that you see. There's a couple different ways to approach every problem. So your homework for this section is this. Flip the page. I want you to do 1A. I want you to do, we don't need to do all of those. 1A is totally fine. Same thing, 2A. No, I don't want you to do 2A. I want you to do, yeah, 2A, sure, 2A. So we got 1A, we got 2A. I want you to do 3A. I want you to do 4. We're going to do 5, 10, and 11. That's your homework for this. They're all just different variations of the examples that I've just done. Use the examples if you need a hand, otherwise, or come see me. Otherwise, best of luck to you. May the force be with you.